All right. How are you going? FHESummit. I'm so happy to be here. Today we're going to do a talk on how to do confidential transactions directly on Ethereum. My name is Aurora and I'll be presenting to you on behalf of ZAMA today, and hopefully you will enjoy my talk. So we're going to have a little quick introduction, a little high-level architecture overview, because it's very important. Who am I talking to? I'm talking to you, future dApp developers. And it's very important to get an overview of the architecture if you want to actually use fhEVM. fhEVM is the library that is behind ZAMA, and we will go into a bit how to use encryption, decryption, re-encryption. Don't worry if you don't know these concepts yet, we will learn them together. And then in the final 20 minutes of my talk, we're going to dive into smart contracts. Because we don't have that much time, let's get right into it. So let's break down the name of the talk first. How to do confidential transactions directly on Ethereum. What do we mean here? We could easily have said how to do private transactions directly on Ethereum. So what is the difference between confidentiality and privacy? Here you can see little circles floating around. So confidentiality basically is the obligation of those who manage information. So it's an obligation of companies or of some entities or even some people who basically have an obligation for other people to store certain information or to keep certain information. This can be a lawyer and lawyer contractor agreement, or let's say doctor-client confidentiality, and so on. Now, privacy more refers to the rights of individuals. So I have the right for my data to be private. And there is an intersection between the two that is basically protection of sensitive information. Why am I so annoying on this? I mean, nobody wants to know about what is confidentiality and privacy. Well, if you start to understand the concept of what those two mean, and if we bring this to Ethereum, what kind of different applications does it unlock? Because confidentiality is very important in normal transactions, in normal life, in lawyer, when you're doing anything with lawyers, when you're doing anything as an entity, as a company, it's very important to have that aspect. So here the imagination is endless, but with basically introducing confidentiality on Ethereum, we have a whole complete new unlock of many new potential applications that you can build, and not all the time build, DAOs and and DAOs and DAOs and DeFi apps. Well, you can build still DeFi apps, but you can build encrypted DeFi apps. So one of the few applications that come to mind are encrypted transactions, and then I put automated encrypted transactions because we have in Ethereum that allows for automation. And then we have confidentiality that is brought to Ethereum that allows for automated encrypted transactions. And already this unlocks a whole myriad of different applications. For example, think of employers that want to pay for their employees and don't want to click all the time for those transactions. Well, we can all automate it on Ethereum. Then we have some other, which I'm going to quickly mention here. We can have encrypted metadata on NFTs or on other information. We can have certain confidential agreements between two or more parties. We can have blind auctions. We can have different decentralized identity system. We can issue passports on-chain, diplomas. We can have things that are processes where you don't have to go physically somewhere or interact with a very permission system, but you can do everything permissionlessly. And of course, finally, confidential voting, which is such a big problem if you guys want to dive into that. It's very, very interesting. Anyways, there are a whole myriad of more applications. I invite you to look into them. All right. So I'm not going to be diving too deep into what FHE is. I already assume, if you're on the FHESummit, that you already have an idea of what FHE is. How we made our libraries is that all this concept is very abstracted away, and you really don't need to know what FHE exactly how it works in details, all you need to know that it allows for performing computations on encrypted data. And we need to know the fact that we have basically 3 different keys. We have the public key. So as we know, with the public key, we can basically take normal data and encrypt it. With the private key, we can take that decrypted data and decrypt it, right? So now it's publicly available for everybody. Before it was not. Then we have something weird in the FHE called the evaluation key. So this evaluation key basically allows us to perform computations on encrypted data. So I can take an encrypted 3 and an encrypted 2, and I can get, with this evaluation key, an encrypted 5. So everything is encrypted, and once I need the final answer, I can basically compute on the private key and retrieve my information. This is all information you need to know about FHE. You can perform computations on encrypted data. The thing that you will probably need to know before you will start building your own smart contract is how the architecture is built and how it works. So bear with me, this is the first time we are presenting this at high level. So there may be some incorrect statements. Here we'll use a lot of abstraction because all the details are really unnecessary. All right, so let's start with Ethereum blockchain, what is really there and what is deployed. So we have our dApp smart contract, and our front end serves as a user interface for interacting with this dApp smart contract. So the smart contract itself will call a set of fhEVM smart contracts, which are deployed on a testnet like Sepolia. So this is all deployed on the same testnet or same mainnet. Afterwards, we'll go to mainnet. So this set of fhEVM smart contracts handle various functionality involving encrypted data and confidential computations. So when we want just to encrypt data, this process is quite easy, right? We have the dApp on the smart contract side, we use the public key, or this can be the front end, we use the public key, and basically we encrypt the data. Very simple. We don't need to go anywhere, right? Okay. So what do we need to perform decryption? So to perform decryption, from the dApp smart contract side, a decryption request is sent to the fhEVM smart contracts, then to the gateway, and then the gateway basically acts as a relayer and relays this information to the KMS. So the KMS here is a key management system. Remember before when we were talking about different FHE keys? So these are all generated on the KMS. So on the KMS, then we decrypt this information, and this information is then visible on the fhEVM smart contracts. This flow would go something like this. The app smart contract, we basically have encrypted information. fhEVM smart contract, gateway smart contract, gateway on the AWS. It is relays to the KMS and send it all back, all basically decrypted and publicly available. All right. How about now if we have a user, and the user wants to access certain information that is, let's say, that only he wants to access and nobody else, right? So we have certain transactions that the user performed, they're all encrypted by the KMS, but now the user wants to see what's his balance, right? What's the flow there? All right. So on the re-encryption side, the re-encryption side basically happens on the front end. So on that front end, the data is basically encrypted with the KMS. So that front end holds the public key of the KMS and the private key of the user. So we send the information from the front end, basically that is encrypted with the KMS to the gateway, to the which relays it back to the KMS. The KMS unlocks it with the private key of the KMS and locks it with the public key of the user. Sends it back to the front end, and now the user can unlock it with its private key. Okay, this is, I promise, the most difficult part to understand. So re-encryption, as it says in its name, is basically decrypting something and encrypting back in a different form. All right. One thing that we forgot about is what if we want to perform computations? So what kind of computation am I talking about? Remember before that we had an evaluation key and we want to perform computations on two different encrypted data sets. Let's say encrypted 2 plus encrypted 3 would result in encrypted 5. How do we do that? Well, we have the evaluation key that is basically held by the coprocessor, and all the computations are basically sent from the fhEVM smart contracts to the coprocessor to compute. This process looks something like this. So we have the DApp smart contracts. It triggers, please compute encrypted A plus encrypted B. We send it to fhEVM, then to the coprocessor, and the coprocessor does the computation and then stores it on basically the result on the database. So encrypted A plus B. All right, and when we will need this information, we can basically retrieve it. Okay, this is all. Let's go on to basically smart contracts. All right, let's get into smart contracts. So when you'll be looking for where to get started, just head on to zama.ai, and basically we're gonna search for fhEVM template. So we have a nice example on a hard hat template, which we can get started with. So you will basically, the standards, git clone the code, and you will basically clone the branch fhEVM 06. This is the current branch that will be stable that will work with Sepolia testnet. Anyways, we cloned the code. I already got the code pre-started. It's fairly simple. If you go to the README, it works like any other hard hat template you're already used to. The only difference maybe is that you have to copy the environmental variables. So do pnpm install, compile for compiling the contracts, and then do pnpm test. That's about it. So let's get started on our first example. And here we have an encrypted counter. So we're gonna do a very simple counter for start. We want to basically increment this counter. So we have an encrypted value, EUINT8, and we start with a constructor which sets fhEVM, fhEVM config, and default config. So we are directly importing the fhEVM lib tfhe.sol library. This is the main library you're going to be working with. We are setting it up on the constructor, and we're initializing our counter as 0. This is not very secure, of course. Currently, we all know how it is initialized. And this one is a bit interesting. tfhe.allow this counter. So here, basically, we are allowing our contract to access this counter value. Otherwise, this computation wouldn't work. So if we wouldn't have this, our computation, so pnpm test, oh yeah, I didn't save it. pnpm test, you can see our computation is now failing. It says exception while processing transaction reverted with reason sender doesn't own LHS on OP. So basically, to perform the computation, we have to allow allow this contract to access this encrypted value counter. If you want to know what kind of encrypted values we have, you can always go to our documentation and check the encrypted types and what do we support. So this is some of the various encrypted types. We have EBOO, EUINT4, EUINT8, and so on. Anyways, here we are using in this example EUINT8 because it's a simple counter contract. So now the fun part. We're doing increment. So we are incrementing, basically, we are performing computations on encrypted data, and we are basically adding a 1 to our counter. So when we are calling increment, we are adding 1 to our counter. And then when we get counter, this is an encrypted variable. So in this simple example, this doesn't help us a lot, right? We are getting something like this. So counter value, but I can show you how the result looks like. So console.log, our counter value, and a little bit like this. I'm using some helpers so we can find it easily in the tests. So here you can see this is our output, and it doesn't help us a lot, right? It's an encrypted value. We don't even know what it is, right? So let's look what we're doing in the tests. Very simple. We are creating some instances. We're using Alice as our signer and basically initializing our contract. And that's about it. We do an increment, we wait for the transaction, and we get some counter out. All right. Let's get now look into some other example. So let's say sample 2, and here I have sample2.sol. I'm gonna delete this. Okay, let's go. So now what happens, what we added here. So we said before, we all know what the value is, right? It's 0. And if we increment it, we can see all in the event history on the blockchain, how many times it was called. It's not very secure or it's a bit useless, right? You can just see how many times somebody called increment, and you can probably quite easily approximate what the counter value is from that. However, if we add an interesting function, increment by, we can have the user add an arbitrary amount to our value, and basically also we have input proof here. So increment by allows us to increment by an arbitrary amount. Let's see how this works from the tests. So we create an encrypted input on our signer Alice, and this encrypted value basically holds the number 5. So our encrypted amount, we encrypt it already on the front end, and we call this function increment by. We put the handle in and send the input proof. So input proof, I'm not gonna go too much into that, but it's basically a validation that we send this data. Anyways, so increment by function just takes this input and turns it into treats it as EUINT8, and we can add this to the counter. So we can perform computations on our data. As a reminder, what we are doing this. So we are basically computing computations on encrypted data, and from fhEVM smart contract, we're calling the coprocessor, and the coprocessor is then saving the things on the database. All right, let's look at now how we would do decryption. So from the dApp smart contract we would call fhEVM smart contract, and then gateway, and then KMS. So what would trigger this? It would trigger a chain of events where the R value would be public for everybody always. Before it was private, now it is public. So let's find our new sample and our new contract, and see how we can make something like this happen. So here we have pretty much everything stays the same. Increment by, increment, get counter stays the same, right? However, we have a new function here called request decryption counter. So what does this do? We call gateway here. So let's look at back here. So we call basically a smart contract that calls the gateway. And we have to add and import a new smart contract called gateway caller. So we are interacting directly between the gateway caller. And how this works, this is an asynchronous operation. So we are requesting decryption counter, and then this basically calls a callback. And in the future, when this computation happens, we can get a decrypted counter. Everybody basically who has access to this contract can get this decrypted counter after this decryption request has passed. Let's see how this looks like. So here I created a little test. We increment the counter contract a couple of times. So in one sample, another sample, third sample, 3 times, 4 times, so 3 times. Then we connect. Our signer, Carol. Carol is another signer. Besides Alice, I didn't want to put Alice, so you can see that anybody can trigger this decryption request if it's created in such a way. And it requests, basically, it calls this function. So this function has this callback function, and we are awaiting all decryption results then. So we are waiting for everything to complete. Then we request to see our get decrypted counter. So we call this function here, and we can see basically it's not encrypted uint anymore. It's a normal uint, and we can see that basically this actually equals 3, right? And if you don't believe me, the tests are passing, right? All right. So let's get into a new, because we are short on time, let's get to our final sample. This is sample 4, and here I want to introduce you to our final concept, and this is re-encryption. So what is a bit harder to understand? So with re-encryption, and it's basically maybe the most useful. So with re-encryption, we don't have to interact with gateway caller. Everything that we are doing is basically mainly on the front end, right? So we are doing increment by. Here you can see that I changed the contract a little bit. So I am just mapping all the addresses. So every address now has their separate counter. It wouldn't make sense for a public counter for everybody. So each address has their own counter. And when we are doing increment, first we check if the counter is actually initialized. If it's not, it initializes the counter to 0. And then we perform the addition to this counter, and same as before, and allow this contract to basically have access to the counter. However, we also allow the user, so message.sender, to have access to our counter. This is a bit different than before. Before we didn't need this, but now that we want our user to basically access this value, we have to use tfhe.allow. It's very similar as before. We basically get counter, and this is we basically are returning an encrypted EUINT 8 and calling it on message.sender. So the idea is if our message.sender will have access to the counter, he will be able to decrypt it, so to re-encrypt it, to see basically what the value is. And the main functionality is here. So here on the test, if you can see, we call increment. This is Alice. Alice is the default signer, basically. So Alice calls increment. Then she calls get counter, sets up re-encryption. So this basically takes her public, private key and signature, as seen basically here. And then we request for a re-encryption of the value. And we can see that the decrypted value is indeed here equal to 1. Let's try this example. We're doing everything the same here as we're doing here. However, the signer is Bob now. So Bob is requesting his own value, but there is Carol who wants to re-encrypt his value. So Carol intercepted his value and now wants to have access to his counter. However, do you think this will work? Well, it does not. So we get an error, user is not authorized to re-encrypt this handle. So let's try to fix this. We switch all carols to Bob. Great. So now that we did this, our tests should pass. Well, amazing. This was all in my presentation. Hope you learned a lot and have a look into more interesting things. Have a look into more interesting contracts and see you next time.